Bismillahirrahmanirrahim. Now we talk about the electrostatic potential, for which we use the symbol U. This is very different from this is independent of the electric potential, for which we use the symbol V. Mean these two are two different terms. So let's start for the electrostatic potential U. Imagine that I have a charge Q1. This is the charge Q1, and here is a charge Q2. At a distance between these two charges are this R. Mean these two charges are separated by a distance R, and here this point is P. It's very clear, in order to bring these charges at a distance um, from each other, bring these two charges close to each other, what I have to do? I have to do some work to bring them there, to bring these two charges close to each other. You can see that if I forgot to put over here, this is positive charge, this is also a positive charge. It could be positive and negative, it could be negative and negative, it could be positive and positive. Yeah, there, because these two charges are positive, they repel each other. Okay, like pushing us, just like a pushing a spring. If you release the spring, the spring get the energy back. So just like that, I'm not saying that these are connected with a uh, spring. I can say that these two charges are connected with the string, would be stressed, and if you cut this string with a scissor, what happened? They fly apart from each other. Okay, mean um, I have to work in there, and that would be called the electrostatic potential energy. The work which I have done to bring these two charges close to each other, and and allow them to connect it with each other, just like this, at some distance, allow them to fix at some distance. I have to do some work. That work is called electrostatic potential energy. So now let's work this out in detail. How much work I have to do, यानी कि for all this, how much work I have to do? Well, we first put Q1 here. The space is empty, just like this. Just imagine this charge only. I have put a charge Q1 at this point. The space is empty. It doesn't it doesn't do any work to place the charge Q1 at this point. Okay, because there is no other force affecting this, repelling or attracting this charge. But now what happened if I come from very far away? Think about it. It is just like infinity, and we bring this charge Q2 from infinity to at this point P. What I have to do is I have to do work. I have to push and push and push until it bring close to each other. Of course, I feel difficulty in pushing to bring it at point P, which is very close to which is at a very small distance r from Q1. Suppose, let's suppose if I am here at this point, at this point, suppose that I reach at this point, what would be the force on me? The electrostatic force pointing toward outward. This is the electrostatic force acting on me. I have to overcome this force. What I will do for to overcome this force, an equal a force is I will exert an equal in magnitude and opposite in direction a force. Let's say this is F1. Okay, so you can see I do positive work. How? The direction in which I'm moving is in the same direction of the force. Mean they can, I have to overcome this electrostatic force exerting on me if I am a point charge. If I'm a Q2 charge Q2, I have to exert the same force in the opposite direction to overcome this electrostatic force. What I am doing positive work because direction of motion and the direction of force are in the same direction. Okay. Now the work done I do is calculated by an integral. Let's say W1 is I am coming from force into dr position vector. The okay. Now see the work is done by going all the way from infinity to r. Okay, the force on me, okay, the force on me is working from infinity to r. So the work done is equal to the force exerting on me dot dr. The work exactly this work is exactly the same as the electrostatic work done by the electrostatic force from distance r to infinity, from r to infinity, F electrostatic force dot dr. Because the both forces are equal in magnitude but opposite in direction, so by flipping over the from infinity to r, the both are same. It does not affect the magnitude. So let's calculate this integral because this is little easy. We know that what is the electric force. How could we know? We know by thanks to Coulomb's law. Both charges are repelling Both charges are repelling because they are positive charges, are they are repelling each other. So the force and R, both charges are repelling. The force F, E, L and the direction of dr, position vector, are in the same direction. They are making an angle 0. So cos theta is equal to cos of 0. Yeah. So we forget about all other factors. Just this is very simple. F like electrostatic force 1 over 4 pi epsilon naught r to infinity dr over r square. If I open up this integral, this one minus 1 over r to infinity, so we get the electrostatic potential energy of, sorry, here I did mistake, q1 q2. What I end up with, the electrostatic potential energy 4 pi epsilon naught r. ठीक है, 1 over infinity is equal to 0. Now if q1 and q2 both are positive, if q1 and q2 both are positive or both are negative, I do positive work. You can see negative times negative is positive and positive times positive is negative. If one is positive and the other is negative, then I do negative work. Okay, so this is the equation for electrostatic potential energy. I want you to convince yourself, if I did not come along the straight line, mean q1 q2, I am q2, if I am not coming from the straight line, following the straight path, what happened if I did not come along the straight line all the way from infinity? Instead, if I am coming from a zigzag way and finally ended up at point P here, I will do exactly the same amount of work. Why? The electrostatic force is conservative force and that is independent of the path. We all know that about, we all know from our FSC that the conservative force is independent of the path followed by the object. So it makes no difference whether I came from a straight line or from any zigzag point and finally ended up at point E. Okay, so it is independent of the path. Now if I do have a collection, I was talking about the point charges. Now what happened if I do have a collection of charges? So we have pulses and negative charges. There are so many positive, negative, positive, negative charges. Now you can calculate the amount of work in assembling all of these charges. I mean, what what I want to say is that if one is bringing from infinity to here, other from infinity to here, and you add up all. Some work may be positive, some work may be negative, but finally you have arrived at the total amount of work that you have to do to assemble all these charges at this point. And that is the meaning of capital U, which we have talking about. That is the electrostatic potential energy. Now, okay, you have to add up all the work done, individual work done by all the charges, and finally you will get the total amount of work done by by bringing all these charges from infinity to the position. Now I turn to electric potential, and for that I start off here with the charge plus q, पिंक कलर यूज करते हैं, plus q, okay, located here at a position, at some position here, and we have some position p at a distance r from this charge. So what I have to do to test this charge, I place a test charge positive q here. It could be positive, it could be negative. We have many times we have this discussion before. So the electrostatic potential energy is q test charge q 4 pi epsilon naught r. That exactly the same that we have. So the electric potential energy is the work that I have to do by bringing this charge plus q here. Now I am going to introduce the electric potential. Sorry for my phone. So what is the electrostatic potential? It is the work done per unit charge. Work done I want to avoid this tick tick you are listening. Work done per unit charge. Okay. Again, what I have to do? I have to do to go from infinity to that position plus q. So what I have work done from bringing the charge from infinity to at position p. So it is the work per unit charge. This little q will disappear if I put the value of Vp is the potential at point P is equal to work done Imagine this little q will disappear. Q 4 pi epsilon naught r. I forgot to tell that the unit of electrostatic potential is joule. Okay, and this is work done per unit charge, so its unit is joule per coulomb. Okay, we can also call this as volts because the guy named as Volta did work all over here. So if we have very simple situation like we have here, that we have only one charge like this, one charge, other is the test charge. Okay, one charge q, then this Vp is the potential energy anywhere, any distance from page 1. यानी कि this is the point where the plus q charge is placed. You want to calculate the potential Vp anywhere at any distance where you want. Okay, if the, you can look into it, R is inversely proportional to Vp. What if you go very far away from this charge, the potential energy is going towards 0. Okay, if q is positive, so if q is positive, the potential energy within space is positive for single charge. Okay, if q is negative, Vp positive, or if q is negative, Vp is negative, यानी कि potential is negative everywhere in space. The work I do in by putting the charge coming from infinity would be negative. Okay, if the charge is negative. Okay, from infinity to at that point P is have to do some work. What would be the potential at infinity due to that positive charge? I said with distance potential is decreasing, potential is slowing down, and at infinity for that positive charge is potential at infinity is 0. So you have positive potential for positive charge, negative potential for negative charge, and if you are very far away, the potential is 0. So if I take an example of Venn graph like a sphere, this is, I will change my color. This is our Venn graph. The radius is r 0.3 meter. Okay, charge on the surface is plus 10 microcoulombs. This charge is uniformly distributed over the surface because this Venn graph is a conductor. What we have learned, E is equal to 0 inside the sphere, so that we can think of all the charge in our being. So all the charge are being at the center of this sphere or distributed at the surface of the sphere. Has in both cases, okay, if I want to calculate mm, what I want, if I want to know what is the potential at this point P, which is at distance r from the center of the monograph sphere. Now we want to know what is the electric field at any point P over here or any point within the sphere. Okay. What I have, sorry. Just ignore this. So if I want to calculate the electric potential Vp, but from R at point P to infinity, F EL or dr divided by Q, Walton per unit charge. So this is also equal to R infinity E dot. Okay. By calculating this integral, we will to infinity. We will get the result of potential at point P, which is 4 pi epsilon naught. The same case as we discussed in our previous lecture. This is for the case R when R is greater than R. This is the situation when R, the point from where we want to find the electric field or electric electric potential is greater than the radius of the sphere. Precisely what we have before. If I put the numbers, mean if this R, what happen if this R is equal to R? So we know that Q is equal to 10 microcoulombs. Okay, R is 30 centimeter. So potential at the surface of the monograph is 3 into 10 to the 5 meters. Okay. What happen if you double the R? R is equal to 60 centimeter. Vp would be 150 kilovolt, almost half of the previous value. For R is equal to infinity, Vp is equal to 0 for all practical purposes. Okay, did you understand? As we go far, if go far from the surface of where the charge is located, the potential will be decreasing. So if I come from infinity to this surface of the monograph or this surface of the sphere, if I am coming from infinity to this surface of the sphere, near to this surface, okay, and I have a charge in my pocket by the time when I reach near the surface. So what I am doing, so work I have done, So work I have done is equal to that charge multiplied by the potential at point P. Okay. If I coming from infinity with a charge at the point P at a distance r from the surface of the sphere, the work I have done is the multiply of that charge with that potential. Okay. Now what if I go inside of this sphere? What if I go inside of this sphere? I will feel no force anymore because there is no electric field inside. E is equal to 0. That means I do not work. Okay, if I do not work from moving from this surface to going inside this Venn graph, this means that the potential must remain constant. So the absence of electric field here implies that the electric potential everywhere is exactly the same as on the sphere, as on the surface of the sphere. Okay. The, so for this special case, I could make a graph of electric potential versus distance r. This is the radius of the sphere. The potential inside the sphere until at the surface of the sphere is same. That's the, if that is 300 kilovolt. If I use the number for the number r is equal to some values with whatever it is. Okay. We have used I think 30 centimeter. R is equal to 30 centimeter. So the potential inside the sphere is constant, and after that it will follow 1 over r. जैसे जैसे हम डिस्टेंस इंक्रीज करेंगे it will going downward. Okay, where r is the radius of the sphere. Now imagine here is we have the surface with equal potential, just like imagine just like in maps, the mountains of equal heights, different mountains of equal height, which we call the altitude. The we have the surface, we have different surface with equal potential, just like the mountains of equal heights. Here we have surface of, now this surface is surface of equipotential. If we have a point charge, okay, point charge is distributed, these surfaces are just like the spheres are concentric spheres. These surfaces have equal potential. That's why these surfaces called equipotential surface. Okay. Suppose that we have more than one charges. What happen if I have more than one charges? We have plus q, we have plus q, okay, and 1, and we have minus q2. For instance, you would be asked that what is the potential at point P? If both, what happened? Think one by one. If both Q1 and Q2 positive, what you will do? You will add the potential due to Q1 plus Vp due to Q2. Okay. Add all the potential due to Q1 and Q2. If Q1 is positive and Q2 is negative, this potential will be negative. Okay. So when you have configuration of positive and negative charges, so depends upon where you are in the space, mean at what distance you are in the space. If you are close to Q1 mean if you are close to positive charge, this will be 1 over r, 1 over r, देखिए, if you are close to uh, Q1 positive charge, 1 over r is 0, and the potential due to positive Q1 is dominating. If you are close to negative of the charge, the potential due to negative charge is dominating. So the total potential is negative in this case, and if you are close to Q1, the potential is negative. So you have surfaces of negative potential and positive potential, equipotential of the negative potential and equipotential of the positive potential. Now I will show you some pictures from your textbook, and we will discuss the equipotential surface at that.